Good evening, friends. I'm sorry there was some technical glitch. We could not start in time. Uh, there are two things which I wish to tell you. One is there is a possibility that some of you may not join the webinar, indicating that the webinar session is full. Don't worry, we have started the recording of this webinar, and the recording would be available immediately today after we get the recorded version of this webinar. And the presentation and our record would be available on YouTube. I will share with you the link wherein you will get this recording. So don't worry, we are there with you. I have today with me Professor Sonawane, who would be talking about the mathematical modeling, the concepts which are related to our project. Friends, before I hand over this to Professor Sonawane, let me tell you few things. One is, most important two things. One is, whenever you wish that your system should be represented in a particular format, and you can have two ways. One is you can have a physical representation wherein you build a system, and after building the system you represent that as a live plant. The second way is to represent it mathematically. Now, the very complex and challenging job for this is how to do it, because we all know that how to develop, design, deploy, install, commission the live systems. So now I'll hand over it to Professor Sonawane, who will take you through this entire presentation and brief you about how to go about mathematical modeling. Professor Sonawane, please.
Hello friends, very good evening all of you. I will take this session, mathematical modeling. The contents of this session is, I'm going to tell you something about why you require mathematical modeling, what is exactly the mathematical modeling, the different stages those are involved in the process of mathematical modeling, the process to solve the mathematical model, the weights, and I have taken few examples to tell you exactly the equations those are used in the mathematical modeling, how to solve these equations. First of all, I must tell you why we require mathematical modeling. So every time it is not possible to have a complete system, physical system. System may be complicated, system may be very simple. So in the offline, suppose we want to test the performance of the system, or we want to test the functionality of the system. So we develop some mathematical representation of the actual system, and that mathematical representation, when you simulate, that will give you exactly how your actual system will be function. So in short, the mathematical modeling is the art. Mathematical modeling is the art, and it is the skill to represent equivalent in terms of the math language. Let us go with what exactly the mathematical modeling means. It's a fundamental and quantitative way to describe and analyze the system and processes. It's the dynamic behavior of the system, processes, which is generally described by the mathematical concept and language. So as I already mentioned to you, it is the dynamic behavior. Definitely, the system is the dynamic system, and the dynamic representation of the system in a time domain form with some equation. So mathematics is a very precise language which will help us to formulate ideas and identify the underlying behavior of the system. It enables to understand and analyze the behavior of the plant process using computer simulation. Once you form the mathematical equations, then after analyzing, after doing simulation, so it will give some analysis regarding how the system will behave, how the system will function. So it's definitely complement to the theory and experiments and often integrate both together. So if you look for the applications of mathematical modeling, these are widespread in fluid dynamics, chemical engineering, process control, computational physics, chemistry, biology, mechanics, material economics, whatnot. So each and every field requires the mathematical modeling. So it's very, very essential to be understand what exactly the process of mathematical modeling. Just look into the mathematical modeling process. It seeks again an understanding of basic science. So the person who is going to develop the mathematical model, they must have the knowledge of basic science, basic laws, basic principles of the system those are going to represent in terms of mathematics. Parallelly, they must have the knowledge of mathematical equations as well. So how to represent my system dynamics in terms of mathematical equation, whether it's a set of partial differential equation, set of ordinary differential equation, set of differential algebraic equation, like that. After representing the system in terms of the equations, then how to solve these equations. So high performance computer. So knowledge of tools, knowledge of computing platform is also equally important in the mathematical modeling. So in short, if you look for these three circles, what I've shown to you, it's a group work, a combinational work of the basic science, computer science, mathematics. So in short, mathematical modeling involves the teamwork. So that's why we have formed the team, and we expect the team, we expect the different participants in the team will be work together and do the mathematical modeling. Now let us go to the types of models. So there are basically two types of models. If you go in more detail, then maybe there are 4 types of model, but broadly there are 2 types of models: statistical model or empirical model. What exactly mean by empirical model? So it is not always possible to find mathematical expression of the reality. Every time you could not say, okay, I have a plant, I can represent my plant in terms of the equation. Most of the time it is possible, but a very, very complicated plant, very, very dynamical plant, where your systems and your variables are changing very frequently. Even though in a time domain, we could not represent such kind of plant in the equations. So in that case, the models are formed from the data collected from the experiments under various scenarios. So you can collect the data from actual plant, gather that data, generate various scenarios, and with the collected data in the lab, we can interpolate the data using some least square approximation techniques or any other interpolation techniques, or maybe the probability distribution techniques, and then derive the relation between a dependent and independent variable. Like very well-known toolbox in the MATLAB, the system generated toolbox, where you can just give the input as a data, and it will be give to you the, based on your choice, whether you want second order model, third order model, accordingly we will get the approximate equations. So that is called data driven model, so or empirical model. Another type of model which is called the mechanistic model or a differential equation model, that actually we are talking about the models in which system behavior is expressed by the set of ODEs and PDEs. So ODEs stands here the ordinary differential equations, and PD is the partial differential equations. So we are representing our system, we are representing our plant. System may be small system may be any complicated system in terms of the differential equations or partial differential equations. And these ODEs and PDEs are formed by applying certain laws of conservation with their initial condition and boundary conditions. Definitely, all ODEs and PDEs require initial condition, boundary conditions. And the laws of conservation may include the energy equations, mass equations, and momentum relations. So let us have some background about what exactly the laws those are applying in forming the mathematical model. So principle of conservation. So the equation that relate the state variables, which is dependent variable, to the various independent variables are derived from the laws of conservation. So in short, the accumulation of S within a system over a period of time. So S stands here either mass or maybe energy or momentum, which is equals to the flow of S in the system over a period of time minus flow of S out of the system plus amount of S generated minus amount of S consumed. So this is overall balance equation. This is overall energy balance or mass balance equation. So if you took the LHS is equal to the right hand side of the mass and energy. So apply any Newton's law or any fundamental laws of energy and momentum, you will get the state of equation at a particular point. Let us say total mass. So this is the mass balance equation. So input total mass minus output total mass over a period of time is equal to total accumulation inside the system. Like that, ddt of rho v is equal to summation of inlet rho fi minus summation of outlet rho fi. So this is a sort of one tank system where density multiplied by flow minus again density multiplied by flow, inlet flow minus outlet flow, summation of total inlet flow minus summation of total outlet flow. Same you can see the total mass balance equation on the component. So this is the energy balance equation again. By first law of thermodynamics, these equations get formed. Flow of internal kinetic and potential energy into the system minus flow of internal kinetic and potential energy out of the system minus heat added to the system minus work done by the system on surrounding is equal to the time rate of change of internal kinetic and potential energy system. So total energy must be same. So this equation is a basic thermodynamics equation. So like that, if you study all these basic equations from which you can form your mathematical model of a particular system. I'll just explain to you what are the different stages of modeling you want. So when you are going for form a mathematical model of your system, what a system is given to you as a project. So we have formulated certain stages. So if you go with these stages, probably you will come up with the mathematical model. It is the offline simulation of your real plant and how effectively you are representing, how effectively you are solving your offline simulation, how effectively you are reaching with the actual solutions. So first stage is a real world problem, then simplify that real world problem, go to the working model, understand all the variables, understand whether variables are static, whether variables are dynamic, how they are going to the saturation, their limits, everything. Note down carefully. Then applying the different laws, what I have explained previously, represent your working model into the mathematical equations. Once you have the set of mathematical equations, choose appropriate tool to solve that mathematical equation. So for that you require some computational model. Maybe your equations are partial differential equations. So partial differential equation cannot get solved directly. So represent that partial differential equation into the ordinary differential equation by applying some approximation techniques. Then simulate, solve that model using the computational tools and test that model by applying the actual scenarios. You should know the plant very well, what type of scenarios. Once you get the results, analyze that results, draw your conclusion. If you are not satisfied, again repeat the procedure. So this is the simplest way, and the different stages, those are involved in the modeling. I'll just elaborate one by one very quickly. So what exactly mean by real world problem? So the real world problem, which is identifying, perform background research, focus on the workable problem. For example, modeling of boiler. Suppose this is the problem. Try to understand what type of boiler, what type of heat input, what is the output, what are the ranges of output, what are the ranges of input, what is the size of boiler. So by understanding the real world problem very exactly, then conduct some investigation if possible. If you have the boiler in the lab, conduct some investigation, conduct some experiment. If not, then how actually you are visualizing your real world problem, you are reaching to your actual solution. Learn the use of computational tool. So like MATLAB, Mathematica, Excel, Maple, Java. These are the computational tools. Those are required to solve the mathematical equation. So in short, understand current activity and predict the future behavior by understanding the real world problem. After simplifying a real world problem, come up with the working model. State simplifying assumption. Maybe you are consider some of the time varying parameters not physically involved. Let's ignore that. Write down all the ignoring situations. So I have considered this situation, I have considered that situation. Maybe assume that your resistance is very, very less than what is your numerator value. So let's ignore that. So you'll come up with some workable equations. You will come up with some simplified equations. So then determine governing principles, physical laws. Identify model variables. So which are the state variables? Which are the control variables? What I'm going to control? Which are the measuring variables? Those are not measuring variables. Those are not measuring states. Can I predict these states? So like that, you can identify all the variables and their interrelation amongst them. After that, express the working model in the mathematical terms. Write down the differential equation form model. Visualize what is the initial condition. Differential equation cannot get solved without initial condition. Let us say what is the initial condition. Whether I want to write differential equation at steady state values or it's a nonlinear kind of things. You have to come up with based on how exactly you are understanding your real world problem. So write down the mathematical equation whose solution describes the working model. So success of mathematical model depends on how easy it is to use and how accurately it obtains. So how accurately you obtain the equations and how the equations you represent in a simplified way. That will give the success of the model. After writing the equations, come up with the computational model. So as I already explained previously, not all the equations are solvable. Let us come up with some solvable equations. What are the tools you are selecting? Suppose you are selected MATLAB. Let's say the MATLAB solvers. We do those equations. See, MATLAB cannot solve second order ODEs. So suppose I have represented my mathematical model in second order ODEs. We have to convert that second order ODEs to the first order ODEs. That is the computational model. Or maybe MATLAB is very difficult. I'm not saying not possible. It's difficult to solve differential algebraic equation. Can I avoid the algebraic conditions? It's up to you how you are representing your mathematical model in terms of the equation. So that is the computational model. So change mathematical model into the form of suitable computational solution. Existence of unique solution. You know, if it's iterative technique, the solutions are multiple based on as you change the case. Let us come up with some sort of nonlinear equations where you are getting the unique solution or you'll get the multiple solutions. Choice of numerical method is very crucial. Choice of the algorithm, whether you are going using the ODE45, whether you are using 15as, 23as, whether my equations are steep, semi-explicit, implicit. Understand the exact nature of your equations and choose the appropriate algorithm and the software. Once you solve your equation, how to test? So apply various test scenarios. That is also true. I could not generate the real test scenarios, but I can approximate my test scenarios into some standard test step inputs, so standard test signals like step input, ramp input, parabolic input, pseudo random signals. These are some standard test scenarios that I can generate in the software, that I can generate in the simulation, and I can test my model. So choice of test scenarios are very important to test the accuracy of the model. Result and conclusion. Once you apply the test scenarios, you will get some result. So meaningful representation of the result is very, very important. As user want to see how your model is working. So it's up to you how you are representing your result. So run computational model to obtain the results and then draw the conclusion. Graphs, charts, even customized GUI and other visualization tools are useful in summarizing your result and drawing the conclusion. It's art again, how you are representing your result and how effectively you are communicating how your model is functioning. After that, you interpret the conclusion, compare with real world problem, how my boiler is functioning. Once I start my boiler, temperature start increasing, heat is generating, it will reach to some saturation. This is the real scenario. Or I'm getting everything the same like by solving my model? If not, if model results do not agree with the physical reality or experimental data, again re-examine the working model. Where we have made the mistake. Suppose you have taken sometime all the assumptions. If possible, relax some assumptions and repeat the modeling steps again. So often the modeling process proceeds through several iterations until model is accepted. Don't expect in the first iteration you will get the better result, you will get the correct result. That's the importance, that's the advantage of modeling. In modeling, you can repeat all the exercise a number of times. That is not possible on the physical plant. Unless and until you are not happy, unless and until you are not satisfied with exactly what result I am getting, repeat the same procedure. So this is the tentative procedure for any system to be modeled into the mathematics in a mathematical way and represent. Now let us come up with, once you have the mathematical equation, very important topic is how to solve the equations. Most of the times you will get equation from papers, you will get equation from some literature, but solving the equation is again a hurdle. You could not expect the existing solvers will be able to solve all the equations, all the models. The exact solution of differential equation represented the model. So the analytical way, first of all, let us try to solve the equation by analytical way, what we learn conventionally from our junior and senior school. So we learn analytical way of solving the equation, but this is only possible if my equations are very simple, written one or two differential equation, that to be a linear one. But if my equations are non-linear, it's very difficult to solve if they contain a non-linearity. In that case, solution methods are limited to small and linear stochastic methods, models only. If the model is more complicated, and especially if the structure of the model is likely to be changed, there is hardly worth even trying to find out the analytical solution. So my suggestion is don't go with the analytical solution. So any type of model equations you obtain, let us go with some numerical way of solving the model. What exactly is a numerical way? Numerical way is nothing but it is the discrete approximation of your equations, which is represented in time domain form. So when analytical methods are unpredictable, we can use the numerical methods to obtain the approximate solution. So it's a approximate solution. Once you know I'm approximating my differential part, so the accuracy of solution definitely depends upon how perfectly you are approximating, how correctly you are approximating. So most of the linear and non-linear models with our solve by the numerical way, but here the choice of discretization and approximation technique is the key for accurate solution. We are learning from our undergraduate. There are numerical methods, allele backward, a range of Runge-Kutta methods, collocation methods. This can be used for discrete approximation. So it's basically the thumb rule or choice. All of you know allele backward is the most stable method, but it requires more number of stages for accuracy. And if you go with the Runge-Kutta methods, probably it's less stable than allele backward, but accuracy is good. So finally, its choice is yours. And if you are using the existing solver, then also where you can select which type of method is suitable. Not all the methods is applicable to all the equations. So understanding the nature of the equations, you have to apply the discretization methods. Let us take one example. Suppose your model is represented by the ODEs. I have taken for your reference is a wonderful model, which is very famous in the literature. That model equation, the simple two equations I'm representing, dx1 by dt is equal to x2 and dx2 by dt is equal to 1 minus x1t square x2 minus x1t. These are the two differential equations representing the mathematical representation or mathematical model of a particular system. Has the two initial conditions x1 of 0 is equal to 1 and x2 of 0 is equal to 0. I want to solve this model over a time from 0 to 1. Now how to solve it? This is just very simple equation. Maybe your model may have complicated equation, but the procedure, the way of solving the equation is the same. As I'm applying for the two equations, you can use the four equations. So this pseudocode is given MATLAB solver. I use here MATLAB ODE45. I have made the function dx1 is equal to x2, dx2 is equal to 1 minus x1 square into x2 minus x1. And I have used the MATLAB ODE45. And simply directly giving the solution as both x1 and x2 over a time period 0 to t. And you can plot it. So the plotting again gives some meaningful that this is the behavior of my variable if my variable I vary from time 0 to t, 0 to 1. This is called as a mathematical representation of your model and solving your model and interpreting your result. If you say I'm not getting my result properly, go again see whether I have taken my initial condition properly or not, whether ODE45 is giving meaningful result or not. So that's up to your study. Let us take another model, which is the differential algebraic equation model. Sometime your system may be characterized by a differential algebraic equation. So this is very critical. We know differential equations has unique initial conditions, but for algebraic equation to be solved, it is mandatory we must have the consistent initial conditions. So most of the solver fails when they have the DAE kind of model. Like that, I have used here, I have studied MATLAB ODE 15 years, 23 years. Those are meant for to solve the DAE type of model. This is a semi-implicit kind of model. Let's say d1 dy1 by dt is equal to y2 is equal, and y1t square y2 t square minus 1 is equal to 0. This is the algebraic equation. 1 is the differential equation. Have the initial condition y1 of 0 is 0, y2 of 0 is equal to 1. I want to solve this model over a time from 0 to 10. When I have used MATLAB solver here, MATLAB 15 years, which is meant for to solve the ODE equations, you have to form some mass matrix. Just learn how to get the mass matrix. Make a function again and pass as an argument some options as a mass matrix as well as what is t-span initial condition, and you will get this result. But look for the result. I'm expecting the model should be solved for time t is equal to 0 to 10, but model is only giving the result up to time 2.6. It means that this particular solver is not capable to solve a model over a period of time from 0 to 10 seconds. But this result is not meaningful for me. If you look for actual result, these are the actual result. So actual result, those are solved from time 0 to 10 seconds. And you got the result only up to 2.6. That's why you can only see this much part in the result. What happened exactly? Because your ODE 15 years or ODE 23 years is not capable to solve such kind of model. So in this case, sometimes it necessitates to write your own solver. You should know exactly what solver is doing in the backend. That's why I'm always repeating. Not all the existing solver can be able to solve your model. It depends upon how you represented your model, how you write down your equations. Let's say I'm just reviewing some numerical concepts of, suppose you want to write your own solver, then you must have the knowledge of numerical techniques. You must have the knowledge of numerical discretization. So you know explicit Euler method. So this is also called as the forward Euler method. Just x of I plus 1 is equal to x of I plus h into f of ti xi. So this is the very simplest way. Explicit Euler method is never results in the set of nonlinear equation, it always results in some equations or solvable equations because I know the value of each and every point at every time. But the error, approximation error is very large in this case. That's why implicit solution, implicit method, Alur method, this is very popular. This is also called as Alur backward method. It is used where I can get, it's very stable method and achieve better accuracy. But the issue for this method, the problem of this method is that once you apply this method, x of I plus 1, t plus 1 is equal to x of I plus h f of t plus 1, x of t plus 1. So I'm evaluating my solution at the next point. So I only know the initial condition. So if you apply this technique, you will end up with a number of nonlinear equations. And your node points is very important. So that is the h. I know final time is 10. If I have only 3 node points, that will be going to be tf by n, 10 by 3. This is my h value. If you are increasing node points, definitely you will be the closest to the solution. So this is the algorithm for explicit, or you can write the algorithm for implicit as well. Like that, this is one problem. So find the y of 0.5 if the solution of initial value problem is y dash is equal to minus 2x minus y. This is my initial value problem. I just want to find out, but note down the equations, applying some techniques, Alur forward techniques, where y of 0 is given minus 1. If you evaluate this model over y of 0.5 for the steps of 0.1, so you will get these equations, and at each and every point you know the value of your unknown. That's why there is no need to solve the nonlinear equation in this case. But if you look the final result, minus 0.7715 is not the exact solution. But for better accuracy and stability, we discretize using Alur backward method and will result in number of nonlinear equations. So this is the first step. Once your ODE is given, you discretize using the best numerical technique, best discretization method, and the choice is depends upon what is the nature of my ODEs. That will result to you the number of nonlinear equations. And once you apply the Newton's method to solve the nonlinear equation, definitely this Newton's method is iterative. And that will give you the solution at a particular time. So you must know the Newton's method. You must know the discretization techniques if you want to write your own solver. So this is the Newton's method. So the root of Newton's method is given by x star is equal to x of 0 minus f of x0 divided by f dash of x0. So f of x0 is the function value at time t is equal to 0, and f dash of x0 is nothing but the Jacobian of your equations at time x0. And if you repeat this, that's why in general you can write x of k plus 1 is equal to x of k minus f of x dash of k, f of xk divided by f dash of xk. So accordingly, once you apply this, it requires either you have to find the inverse of the Jacobian, or you have to solve this system by linear way. So the knowledge of how to get the inverse of matrix, knowledge of how to solve the linear system is also important in this case. Now you understand what are the important factors when you write your own solver. So understanding the numerical techniques, understanding what exact Newton method works, how to get the set of equations, from that the Jacobian of the equations, inverse of that equations, or maybe the solving by the linear way. This is the summary for the Newton's method. So this is Newton's method applied to the set of nonlinear equations, and this is the Jacobian, and in general the equation is represented like this. And this is the Newton's method algorithm for system of nonlinear equations. So thank you so much. I'm just handing to Professor Agassi. He wants to elaborate more on what exactly the mathematical modeling and its use. Thank you.
Yeah, thank you, friends. There are few things which I wish to tell you. One is Professor Sonavane explained you in detail about what a mathematical modeling is all about. Now, I'm going to brief you about how this can be used in your projects. Now, this project can be from any category. It's not that the project which is related to mathematical modeling, you have to apply these techniques. But a project even like development of a special purpose machine, these techniques can be used. Now, how can we use it? For example, I'm just taking one example just to explain you the importance of this mathematical model, because one of the deliverable, if you have read the deliverables carefully, you will find that one of the deliverable is the walkthrough model, 3D walkthrough model. Now, what is that walkthrough model is all about? These walkthrough models are true representation of mathematical form of equations which are running at the back end, and the user interface will give you an impression that as if you are running through that machine. For example, I wish to develop a special purpose machine for mango pulping. I'm just taking an example. Now, this can be applicable to any project which we have listed already. So in case of a mango pulping, I wish to know how much is the heat energy which I need, because I have to calculate the size of the heater, or I have to identify what should be the solar system which I should depute for. Now in this case, you need to know the volume of the pulp which is available, the extent of density which you want to reach, and in how much time. Now all these functions put together will give you that to achieve this function, you need to add this particular type of energy to be given to the system. Now the question is, if I solve these equations, if I put these basic and fundamental equations, I can calculate the heat energy required. Then after playing with the heat energy, I can immediately get the reduction in time and the rise in density if I change heat input. Now this is the best way to use these techniques. Take another example. The other example is related to the project in which you have development of a water grid. Now whenever somebody is developing a water grid, he or she needs to know the hydraulic model. Means the water is stored in an elevated storage reservoir, and from there it is distributed to the consumers. Now depending on the height at which you are located, the flow of fluid will be decided. Now if somebody wants to know that I have to ensure that each consumer will get equal amount of flow, then you have to develop a system which will ensure that the sufficient hydraulic head is available, and where the head is rising, how to reduce that head and convert that to the customer who is facing difficulty for the flow. Now, friends, what we now will be doing after this webinar is, this webinar is recorded already. We will be putting this on the YouTube, on this UEP Media Center. We will be sending this link to all the students, those who have registered or participated in Integrated Technology Olympiad. So this link, if you click on that link, you will see the presentation. The second most important thing is related to those who are working on pilot plants. Now somebody who is working on pilot plants, maybe by referring to various papers, he will get some information about these pilot plants. But we will be giving you actual demo of the pilot plants if you wish to do so. Now the only condition for this is you or your group member must send a request to your mentor and book a slot for the demonstration of these pilot plants. You can start sending your request immediately after the webinar. We will register your request and we will send you the slots, wherein through a Skype session or any other session like this, like a webinar session, we will demonstrate you how the plant is working. Friends, please understand, to all these plants, a camera is connected. So we will physically, if you are not physically there with us, we will take you through the plant and all the details, and we will have question and answer session also, so that you will get more insight about these plants. But this is only on the request. I hope you must have enjoyed. My apologies once again for the inconvenience to all those who registered for the webinar but could not participate because of some technical issues at our end. But believe me, we are always there with you. We will support you. We will guide you. Your mentors are always with you to ensure that you are on the right track. Thank you so much. And now I'll close this webinar. Thank you. Stop recording. Start recording.